Hey, honors pre-calc, welcome to lesson 2.4, complex numbers. Complex numbers include potentially a real portion and a non-real portion, which introduces us to imaginary numbers, the number I. You should already know about square root or radical functions and what a conjugate pair is, and if you don't remember, that's okay because we'll go over it. And here's what we're going to do. You're going to add, subtract, multiply, and divide complex numbers. And students will solve equations involving complex numbers. Today's essential question is, how do you represent the square root of a negative number as a complex number? And you'll be able to solve an equation like this that doesn't factor nicely and has non-real zeros. And you'll be able to find a way to represent what those are using complex numbers. All right, so here are our notes for 2.4 complex numbers. First of all, you need to know that radical is just another word for a square root. And a simplified radical means that there are no remaining perfect square factors. We've been doing that a lot so far this year, so hopefully you're okay with that. We're going to be needing to know the perfect squares, so I listed them on here for our benefit, and here are all the prime numbers, so you can tell if you have prime number factors when you're trying to reduce your square roots. That brings us to the imaginary number I. Up until now, if we have had the square root of a negative number, we just say, hey, that doesn't exist. It's not part of the domain. We don't include it in our answer. We say no answer or no real number. And now we're going to say that the square root of negative 1 can be represented by the variable I. And we'll see how that works. So if it's a complex number, so it might have imaginary and real components, we always list it as A plus BI. B and A are some number, or they might have X in them, something. The I always has the imaginary component, and the A would always be the real component. Okay, so here's an overview of all of the types of numbers, and there's real numbers and non-real or imaginary numbers. Real can be broken down into a lot of different types of numbers. You can read over this to review that if you would like. But today we're going to be mostly focused, obviously, on the non-real numbers. These numbers can't be found on a number line. For example, the square root of negative 1, which is I. However, we do want to keep track of it because if we ever get into a situation where then we want to square the I squared is negative 1, right? Because if you take the square root and you multiply it by another square root, then the square roots cancel out. So we're left with negative 1, which pops it then into the real number realm. So that's why we want to track imaginary numbers. Also, I cubed equals negative I, and I to the 4th equals 1. And then the cycle repeats. If we wanted to write that down, think about it like this. So I is I squared is negative 1, I cubed is negative I to the 4th is 1, I to the 5th, it's like I to the 4th times I. So we just get 1 times I, or I, and then it just kind of, the cycle repeats. So it's these 4 things over and over. So it's I, negative 1, negative I, 1, I, negative 1, negative I, 1, and it keeps going, okay? We're not going to get too much into that, but that's how that would work. So example 1 here is just about adding and subtracting complex numbers. And I think you're going to be happy with this section because it's really just kind of doing what you would do with normal variables, all right? So in the first part, we have 4 plus 7i plus 1 minus 6i. And the real portions, the 4 and the 1, can be combined by combining like terms. And the 7i minus 6i can be combined just like normal. And so we're left with 5 and 1i, like that. In letter B, same idea, except now we have a minus. So I'm going to change it to a plus and distribute the negative. And now we have 1 minus 4 is negative 3, and 2i minus 2i goes away. So the imaginary portion canceled out in that one. We're just left with negative 3. In letter C, same idea. Anytime we have a negative in front of parentheses, we're going to distribute it to inside. We have, I'm going to do the real portion first, and we have 2 minus 2. Okay, so the 2's canceled out. the i's, there's 3i, minus 3i, minus 5i, and that leaves us with negative 5i. And for this last one, let me distribute the negative. We have 3 plus 4 minus 7 is 0. And for the imaginary portion, we have 2i minus I, which is also 0. So this one canceled out completely. So anytime that you have a real and an imaginary portion, we want to write the real portion first, then the imaginary. And if we only have one or the other, we only have to write what we have. And if we have none, we can just write 0. All right? So that's how you add and subtract. Next up, we're going to see how we multiply complex numbers. So let's look at letter A. When it's a simple kind of distributive property, we just distribute just like normal. So we're going to get negative 8 plus 12i. In letter B, we're going to FOIL. So we have 2 times 4 is 8. 2 times 3i is going to be 6i. Negative I times 4 is going to be negative 4i. And negative I times 3, positive 3i is going to be negative 3i squared. So we can combine like terms and we get 8 plus 2i minus 3i squared, but we're not done yet because remember on the first page we said that I squared equals negative 1. So this is really 8 plus 2i minus 3 times negative 1. That's one of those cases where you want to keep track of the i's, the imaginary numbers, because some of them turn real in some cases. So let's kind of finish this up. We end up with 8 plus 2i plus 3, which is going to become 11 plus 2i. In letter C, it's another FOIL question. We'll get 9 minus 6i plus 6i minus 4i squared. The plus 6i and minus 6i canceled out, so we're left with 9 minus 4, and that I squared can become negative 1. So we have 9 plus 4, or 13. And in letter D, 3 plus 2i quantity squared can be rewritten as 3 plus 2i times 3 plus 2i, and we want to do that because now we see that we have to FOIL. You don't just square the 3 and square the 2i, right? We know that. Okay. So we end up with 9 plus 6i plus 6i plus 4i squared, which is 9 plus 12i plus 4 times negative 1. So it's 9 minus 4 is going to be 5 plus 12i. There you go. So that's how you multiply. Really, anytime there's I squared, it changes to negative 1. All right, let's keep going. Dividing complex numbers. Okay, so dividing is a little trickier because there's no FOIL that works for dividing. It's not that simple, and in order to have a simplified answer, we want to be able to write it as a complex number in a plus bi form. So if there's an I in the denominator, we have an issue. So in order to solve that, we're going to do something that consistently always gets rid of an imaginary portion of a number. And it's just like actually what happened in letter C up here in example 2. Notice that we have 3 plus 2i and 3 minus 2i. Those are known as conjugate pairs because the plus between the two terms was switched to a minus. That's what a conjugate pair means. And it's useful because it gets rid of the outer and the inner terms from FOIL. It always gets rid of the outer and the inner when you multiply and add. And that, in this case, that's the only place where the I is sticking around. So the fact that it canceled out is perfect because then we just get a whole number, no imaginary portion at the end. So that's what we're going to do here in example 3a. We're going to multiply specifically to get rid of the I in the denominator. So I'm going to multiply by 1 minus I and 1 minus I on the top and on the bottom. Now we're allowed to do that because if we're multiplying by the same thing on the top as we are on the bottom, it's really like we're multiplying by something divided by itself. So we're not changing the value of the fraction because we're doing the same thing on the top and on the bottom. And once we do that, on top we end up with 1 minus I because we distribute 1 and nothing changes. And on the bottom, we're going to get to FOIL. So we have 1 times 1 is 1. And then we have the outer and the inner, which cancel out. I'll write it this time just so we can see it. So it's going to be minus I plus I. And then I times negative I is going to be negative I squared. So we end up with 1 minus I over 1. Those cancel. I squared becomes negative 1, so it really becomes 1 plus 1. So we get 1 minus I over 2. And to officially write it as A plus BI, I'm going to separate this into 1/2 minus 1/2 I. So 1 over 2 and the I over 2 can be separated. I over 2 can be written as 1/2 I, right? Now, that's allowed because when there's a one-term denominator, the numerator can be split, and each numerator will have the same denominator of 2. The initial one had a common numerator and a 2-part denominator. It doesn't work backwards. I can't split this because the 1 is divided by 1 plus I, not divided by 1 and then divided by I. So that's kind of stuck. All right, let's try letter B. So for letter B, we're going to multiply by the conjugate pair of the denominator because that's where we're trying to get rid of the I. We're going to multiply by the same thing on top and the bottom so that it cancels out and leaves us with the same as the original. And let's see what we get. So on top, we're going to have fun foiling this. 2 times 4 is 8. 2 times 2i is going to be plus 4i. 3i times 4 is going to be plus 12i. 3i times 2i is going to be plus 6i squared. On the bottom, we'll get 4 times 4 is 16. If all goes well, the outer and the inner should cancel. So we have 8i minus 8i. I'm not going to write it this time. And then we have negative 2i plus 2i, so negative 4i squared. So on top, we can combine to get 8 plus 4 plus 12 is 16. 16i. Yep. Okay. And then we have 6 times negative 1, really. So that can be minus 6 over 16 plus 4, right? Because the I squared becomes negative 1. Next step, 8 minus 6 can be 2 plus 16i. And on the bottom, we have 20. All right, so last step, I'm going to separate this, that it's really in the form of a complex number. So we have 2 over 20 plus 16 over 20i, which can reduce to 1/10 plus 4/5 I. All right, last step. Well, nope, just kidding. There's 2 more examples. We're going to look at example 4 next. Combined operations. Perform all operations as indicated. So in this first question, we have the square root of negative 3 times the square root of negative 12. Now this is very important. Whenever we are multiplying 2 square roots and they might have negative numbers inside, if we just follow our normal square root properties and multiply negative 3 times negative 12, we would get what? 12, 24, 36. We would get square root of 36. And the negatives would cancel. But then that kind of leaves out the fact that the negatives were there in the first place, and they really do mean that we have imaginary numbers built into this. So what we need to do before we combine any square roots is we want to pull out the I before we even start. So I'm going to think of this as the square root of negative 1 times 3 and the square root of negative 1 times 12. And then this is really now I root 3, and this is really I root 12. So I'm pulling out the negative square root of negative 1 and making it into an I. Same thing over here, I'm pulling it out. Whenever we have a square root and an I, it's common to put the I in front to the left of the square root. Otherwise, if you write it on the right, it's easy to accidentally think maybe it's underneath your square root line, but it shouldn't be. So I like to write it in front. This multiplies together now to get us I squared times the square root of 36. Now we can combine. And then let's see, I squared is -1. So we have the negative, and the square root of 36 is 6. So our answer is actually -6. All right, let's try letter B. In letter B, I'm going to pull out the negative first. And then we got to reduce these square roots. So square root of 48, let's see, it is 12 times 4. And this is 3 and 4 and 2 and 2 and 2 and 2. So we have 2 pairs of 2's, so a 4 can come out with a 3 left over inside. So to write that, we would usually write it as 4i root 3. So the 4 comes in front of the I, the 3 stays in the root, the I just kind of hangs out there. Do the same thing for the 27. 9 times 3, 3 and 3. So we have a 3 that could be pulled out, and there's a 3 left over inside. And now you can see that these are actually, in a way, like terms that can really be subtracted, right? We have 4 I root 3 minus 3 I root 3, and that's going to equal 1 I root 3, or just I root 3. I root 3. Okay, let's take a look at letter C. We have a square here, so to make it clear, I'm going to write it out twice. And I think maybe we should change this square root of -3 into I root 3 before we even start. So we don't accidentally multiply it incorrectly. And now let's see what happens when we FOIL. So we have -1 times -1 is 1, negative minus I root 3 minus I root 3. Oh geez. Okay, so then we have plus I squared times root 3 times root 3, which is 3, because the square root of 9, so it's 3. So now we have 1 minus 2 I root 3's minus 3, right? Because I squared is -1, so it's minus 3. And we end up with -2 minus 2 root 3 I, which I'm going to write the I first. -2 minus 2i root 3. There you go. Last question. Now we have the last example. Example 5, solve equations involving complex numbers. So if we have something that is equal to 0, let's just solve for x. So we can subtract 4 since there's only one x term. And now we are taking the square root. So x equals plus or minus the square root of -4. That plus or minus is still key, even though we have the square root of a negative number. We initiated a square root, so we write the plus or minus in front. And now we know how to reduce this. So we might pull out the I and make it root +4, and the root 4 is 2. So this is really plus or minus 2i. In letter B, we are not so lucky. We have an x squared term and an x term. This is a quadratic, and it does not factor. And so what we're going to have to do is use the quadratic formula. So we have a, b, and c. A is 3, b is -2, c is 5, and our answers are going to be plus or minus. What am I doing here? The plus or minus isn't at the beginning. X equals, whoa, I'm going crazy. Okay, give me 1 second to look it up. All right, I looked it up and I wrote it down. I don't know why I forgot that. I think it was just me being recorded and freaking out. I don't know. But we've got x equals -b plus or minus the square root of b squared minus 4ac all over 2a. And so we have to plug in a, b, and c in order to solve for the zeros. So let's try this. We got -2, which is 2, plus or minus the square root of b squared. So -2 times -2 is going to be 4. minus 4 times A times C all over 2 times A. Okay. So let's see what happens here. We got 2 plus or minus square root of 4 minus 4 times 3 is 12 times 5 is 60 all over 6, which is going to be 2 plus or minus the square root of negative 56 all over 6, which is going to be 2 plus or minus, we got to pull out the I, and then the square root of 56, that's divisible by 4, 4 times 14, so we have 2I root 14 over 6, and you can write out your factor tree for the 56 if you want. The negative is the reason that this I is here. We have a pair of 2's as factors of 56, so 2 can come out and 14's left over. And then for the last step, I want to just write this in a nicer format. So 2 over 6 becomes 1/3. The 2 over 6 again becomes 1/3. The root 14 does not get divided by 6, within the root. So it's going to stay 1 root 14 over 6 I. And you can write the I in front if you want, but that's what we get there. Again, the 2 over 6 becomes 1 over 3. This 2 over 6 becomes, oh my gosh, I wrote a 6. That 2 over 6 becomes 1 over 3, which makes this denominator 3. The root 14 stays up there, and then we have I. Okay, there's our answer for that one. All right, so now you have everything that you need to know for the worksheet. I don't have anything separate to tell you about this worksheet. It all should make sense based off of this notes. You will need the quadratic formula, I believe. Yes, for 2 questions on the back. So make sure you write that down. But other than that, I hope that everything works out. And if you have any questions, please let me know. Thank you very much for watching.